Okay, we're back. We're going to do some algebraic examples now. Algebraic examples, we're going to evaluate, which is a better word for compute, each of the following. So here's the first one. Let's do the limit as x approaches 2 from the right of x minus 2 over top of x plus 1. Now, depending what tools you have at your disposal, if I'm going to do this algebraically, what I'm going to do is I'm going to set up a chart. And what I'm going to do is I'm going to choose some values that are greater than 2, but pretty darn close to 2. So maybe 2.1, 2.01, and 2.001. And I'm not going to put too many in because I want to see what the trend is. I could keep going forever, and that really would be a waste of time. So I'll put in 3. And then what I should do is I should put in my function. So that's the expression that we have to evaluate now. So what I'm doing is I got to take 2.1 and plug it in for x. So 2.1 subtract 2 is 0.1, and the bottom is going to be 3.1. So it's going to be 0.1 divided by 3.1. So you're going to grab a calculator. 0.1 divided by 3.1, and I get 0.03225, yada, yada, yada. The next one is going to be 0.01 over 3.01. So 0.01 divided by 3.01, and I get, oh, it's a small number, and my calculator's in scientific notation. See that? That's scientific notation. So you should know to move that decimal over, but you know, we all hate that. So I'm going to go under mode, and I'm going to change it to normal mode, and it's going to give it to me in this form. You need to learn how to use your calculators. Okay, so it gave me this nice number, 0.0333225. What's important here is notice that there's a multiple of 10 that it's been reduced by, right? So it's been divided by a multiple of 10. The next one is going to be 0.001 over 3.001. So it's 0.001 divided by 3.001. And the important thing to notice is this is getting smaller and smaller and smaller. And so we can assume from this, since I've been choosing values that are pretty darn close to 2, so I didn't choose values that were larger than 2 and far away where things could change. I chose things really, really close to 2. And assuming that nothing changes in the graph, that I've chosen a good starting point close to 2, then we can assume that this will continue, and it will continue to get smaller and smaller and smaller, and it's going to approach 0. And I think that's a very good assumption. And so what we would say here is that the limit as x approaches 2 from the right of x minus 2 over x plus 1 is going to equal 0. And that's your answer. And that's how you do that question. That's algebraically. Now, we could also do it using Desmos, and I leave that up to you to do because it's going to take me a long time to flip between screens. But on Desmos, if you were to graph x minus 2 divided by x plus 1, look at that graph, and then you can approach it from approach 2 in your domain from the right, you should be noticing that you're approaching 0. And I leave that up to you guys to check out on Desmos. And do that, because I will let you use Desmos at different times to figure things out. So let's take a look at B now. Here's another example. Why don't we do the limit as x approaches 0 from the left of 1 over x. Now again, if I'm going to approach this algebraically, then a table of values. And a table of values is ultimately the most basic tool to use on limits, and you're always going to use them on left-handed limits if you're doing something algebraic, or not just left-handed limit, one-sided limits. So I'm going to choose values that are less than 0 So they need to be less than 0, but getting closer and closer to 0. So I'm thinking these might be some good values. And they might be horrible values. You have to have an understanding of what your function looks like. Now, I know what that function looks like. That function looks like this. Okay, that's what that function looks like. And I know that this is 1, 1, and this is -1, -1. So I know that I'm picking values on the right-hand side of 0, that nothing funny's happening, right? They're not taking off, they're not oscillating. It's a nice, smooth, continuous curve. Talk more about that later. And so if I put in the range value, it's going to be 1 divided by 0.1, so that's going to be 10. That's going to be 100. That's going to be 1,000. And since there's no reason to think anything's going to change, as I keep allowing x to get closer and closer to 0 from the left-hand side, then I am going to, hold on, something's bothering me. Something's definitely bothering me. I'm approaching 0 from the left. This isn't from the left. This is absolutely wrong. This is not. This is approaching from the right. This is absolutely wrong. This should be, I'm glad I made this mistake. I am not embarrassed by this. This is a good thing. If I want values that are less than 0, it's going to have to be negative 0.9, negative 0.909, negative 0.009. Does that make sense? No, I wouldn't use those points. Those points are no good. I'd use these ones. Negative 0.1, negative 0. There we go. That is on the left-hand side of 0, right? And getting closer and closer to 0. So if I do a number line, and here's 0, what I've chosen is, maybe this is negative 0.1, this is negative 0.01, this is negative 0.001. Everyone has to make that mistake at least once. That happens. So I've got mine out of the way. It's not going to happen again. So this is wrong. These are values of x that are greater than 0. These are values of x that are less than 0. So 1 over x is going to be negative 10, negative 100, and negative 1,000. So what's happening is this one is that one. So if we were to continue, we would notice that this would continue to get larger and larger and larger negatively. And we would say that this does not exist because infinity is not a real number, but we would put this in so we didn't lose that good information. And notice it's right here. As I'm approaching 0 from the left, that's what that is. X is approaching 0 from the left. The f of x value is taking off down, 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 down to negative infinity. And this one over here, use a different color, so 0.1, 0.01, so that's on this side. So there's 0.1, there's 0.01. That one in there is 0.001. This one on this side, you'll notice, as x approaches 0 from the right, you'll notice that y is approaching positive infinity. Didn't ask for that, asked for the left, and I almost goofed up. So I'm glad I did that. I'm glad you were able to see that. And notice I found my mistake because I knew what the graph should look like, and it wasn't matching up. So there's an example of being aware of what you're doing, and if you make a mistake, self-correct. That's what I want from you guys. Stop the video there, and so I can get set up for the next example. Oh, by the way, just in case, so if someone had asked you this question, so this is the limit as x approaches 0 from the right of f of x, does not exist, but it goes to positive infinity. And if anyone was to come along and ask you for the two-sided limit of that, if someone was to ask you for the limit as x approaches 0 of f of x, you would say, hey buddy, it doesn't exist. And I can't tell you that it's approaching 0, or I can't tell you that it's approaching infinity or negative infinity, because it depends on which side you're approaching 0 from. So that's the best I can tell you for the two-sided. That's what I can tell you from the right-sided. That's what I can tell you from the left-sided. There you go. We'll be right back.